So I'm actually a mathematician, but I'm working now as a programmer, and I'm really happy with PureScript and with functional programming. So I will have a short introduction for Comonads and what are the Cofree, what is the Cofree Comonad, and then I will show you the React Router version 3, because now it updated. There is a new version which is totally different, but the third version had a really nice interface. And then I will present a piece of my library that I wrote to model the React Router with a Cofree Comonad, and hopefully at the end I'll be able to present a simple isomorphic React application that is using Hyper library as a server, and it renders the React application on the backend, and it's using the Cofree router on both backend and frontend. So, what are Comonads useful for? They're really useful for tracking state or getting some information in some way. For example, very simple thing that we will see in next slide, that you can model streams with Comonads. You can also write interpreters using, for example, today we had this example how to build an interpreter, a DSL using the free monad, and if you have a functor that is dual to the functor that makes your DSL in the free monad, then you can actually build an interpreter using Cofree Comonad, and which has some nice applications. Then you can also model UIs using pairing between monads and comonads, and Phil Freeman has a really nice repo on GitHub about it. So if you're interested, definitely check this. And well, routing, really. And yeah, like 2 days ago, I tweeted that I will have a talk about it, and some people complained that I will use comonads for routing. So I will convince you that it's not unexpected, actually. Yeah. So what's the definition? So I just copied this from PureScript library, from the I think PureScript control. So first class is the extend class that is built upon a functor. So W has to be a functor, and you have one function that is called extend. And it has this dual signature than what you get in bind when you're working with monads. So instead of in bind, you would have a map from A to M of B. Here you have the dual, so from WA to B, and you can extend the monad, the comonad, using this arrow. This gives rise to some nice compositions that you can have. One is that you have co-Kleisy arrow and duplicate. I put the duplicate only because I'm a mathematician, and this is the important bit, actually. So, but those two definitions are actually equivalent. You can write a simple proof that you can derive one from the other, and the axioms correspond to each other. Maybe it's a little bit easier to say what is associativity when you have this duplicate. And then Comonad has extract method when you can extract something from Comonad. And this gives really nice, really interesting difference from monads, where in monads you can put something into a monad. So you can turn an object into a monad with the pure function. And here in the Comonads, you can extract things from them. So they usually actually come with sort of environment that they have something inside of them, and you can get it out. And a very basic example is a stream Comonad. So the data type is just has a one constructor, cons, where you put a value a, and you have the tail, which here we have to use in PureScript. We have to use lazy for making it lazy, because otherwise it would be just infinite data structure. So it's a functor. You can derive it, and the functor structure just maps over the A's and all over the A's that are coming later in the stream. The extend map is very similar actually to the map, to the functor instance. Just the difference is that you have access to whole stream at every step. So you can change the stream. You can extract value not just from the single A, but you can be non-local and extract things from other A's. And the extract method is very simple. It just extracts the first value. So a simple application of this, how you can use extend, is a smoothing operator on a stream of integers, or stream of numbers actually. So the first argument of the smooth function is for how many slots of the stream we are looking for. For example, for first 10, and we want to average. Construct a new stream that averages 10 values from the original stream. So we can just sum n, just sums first n values and average n averages them, and then you can use extend to get a stream, and that's how the Comonad machinery works. And this is actually an example of a free Comonad, or Cofree Comonad, where it's generated by the identity functor. So the Cofree Comonad only complicates in the way how you can how you construct the tail of the stream. So if you take f, the identity functor, you get a stream that we had. If you take maybe, then you would get a stream that finishes at some point. And if you What? You
can reconstruct list, linked
list. Yeah. This what you have here is a linked list, but it's a lazy linked list. Yeah, you can take a function as a functor where then the tail will depend on some argument or. Yeah, and there are some combinators that are nice to work with, like the make Cofree. It just if you have the element and the tail, you can just put together and get the Cofree. You can get the head and the functor, extend, and the extract are really the same as in the previous example. They're not more complicated in any way. So in the functor instance, you have access, the f function has access to each value. In the extend, you have access to whole Comonad, and the extract is taking the head. So it's really the same what it was in the previous way, in the previous slide. One way of thinking about Cofree Comonad is to think about it as a tree that is spanned by the functor f, and which is annotated at each step. That's why they are really nice for tracking state, because you have this A that can track a state. So now a little bit about React. How many people knows anything about React? Okay, some, but not everybody. So React is a library for building UI interfaces. It uses JSX syntax in JavaScript, which is basically a little bit like XML syntax inside JavaScript, and each tag is a component. Whereas when you compile it to JavaScript, it just calls a function that creates an element, which is a simple JavaScript object from a React class, which describes how the component behaves. And those React elements form a virtual DOM. So something which looks like a DOM, but it isn't. And there is a nice project to build React router, to build a router for React application using very similar syntax. And you basically declare a router component, and you declare what kind of history you want to use. In this case, the browser history. So it will just track the state of the history, and then you define your routes, and they can be you can have multiple routes, and they can nest inside each other. So it's the same as building actually a DOM tree, and you declare the path that they will mount on. So if, for example, if we are on a home /user/10, then the main component will match. It will be mounted in the DOM, and inside it will receive children that also matches the path, which is in this case just the home component, and the home component would get the children that matches the path again, the rest of the path, which is the user. So it will mount this path into the DOM. So actually looking at this, you can see that this is actually Cofree Comonad for the array functor, where the route is some type of this route, and Cofree array, you can actually use it to model DOM, because this is how DOM looks like. It's you have the HTML element, and then it has its children, so a list or array of children that can have arrays of children, and this is how the DOM looks like. So it's actually not that surprising that you can use Cofree array as for modeling the router. there are 2 slides about the library, and it needs to know about a class you want to mount at each path. So the first type is the type alias for the class you want to mount, but it also needs to know how to build the properties for this given class. So in React, classes get properties, and they're sort of like functions from those properties to UI. Well, they can hold a state, but that's not important for this talk at all. There is a route props class which just says how to build the properties for a given argument, because in here this every path we will use. I use in this library PureScript router library for parsing the URL, and it's a really nice applicative parser. And as with any applicative parser, you will get different objects for different routes. So this arc is the location kind of thing that you need to you will get from the URL. Then is the route and index route. Will ignore the index route, but the route is just a string which is basically an identifier, a name. Then the routing match, which is the parser that will match for a given route, and the class that you want to mount at this location. And a router is a Cofree array of tuples, where the first thing is the route, and maybe you want to have an index that we're gonna ignore for now. And there is this colon plus combinator that you can use when you want to create routes that do not have index. Otherwise, you can use the colon greater. So how the interface looks like, it's very similar to the React router. It's just you use the route type to create routes. Well, there is an error. There should be unit before delete, but that's okay. So this is the combinator from the parsing library, and the main is the main, home, user, book, and settings are React classes that you want to mount in those locations. And so that's pretty similar what it was in React world. So now something very some internals. So the main thing in the router is how you want to match the routes, and it takes a route which is basically a parsed URL into sections, and a router, and it gives back maybe Cofree array with information about the route. If what's the URL, what are the properties, what's the route, which says which class we want to have at this position, and what's the index. I've hidden what's the shake function in this definition. It's not important. The more important thing that I want to speak about is the go routine, which is a kind of recursive function that goes through the Cofree array Comonad, and it basically unwraps what it needs to unwrap, and then it runs the matching function against the URL that we have, and then if that matches, the matching library returns the rest of the URL that we want to pass further to the children, and the argument that was parsed from the URL, and then we just build the properties and we return just of things that we found, and we go inside the array. And if nothing was found, we just return nothing. And at this point, you can wonder, yeah, but why not to use extend? Because this would be the really nice application for it, and you could actually do that. The thing is that we need to trace a state, the array of arguments that were already parsed, and the rest of the route, the rest of the URL that's still to be parsed. And we could use this extend m function, which basically runs a sequence over extend, with tracing the state in a state monad. But the problem is that it wouldn't work, because it would update the state in wrong positions. Like before, here we only want to change the state when we go inside the array, not when we parse for other children. There might be another way around this, but this would change the types and wouldn't be that the types wouldn't be that simple, I think. So I prefer to stay with this. There is a run router function which just runs the router. It basically matches the routes, and then from this maybe Cofree thing creates a React element, which is like a very basic routine. Okay, let's try to do a live demo. Yeah.
So, we have Cofree. When I think about Cofree, I think about co-data as opposed to data. And when we said, when I looked at routes, I'm thinking, well, am I possibly going to have an infinite depth of routes? So I'm curious, have we taken advantage of the fact that it's co-data and not data? I might have missed it in the slide yet. I mean, for routes, it's valid to represent it as data, just as much as it is for co-data, and we've lost the functionality that you showed.
Well, the problem, you would have a problem to get an application that really takes advantage of having infinite routes, because
right, yeah.
it's
right.
So just so this is a very simple application. It has just two routes, which is one nested in the other. There is home. Where's my mouse? Okay. We are at the home, and there's the route that shows information about somebody, and you can also um, you can add well, let's put Miles Davis. And you can reload, and the data is still there because it's this application is using kind of Redux architecture that I wrote. It's called Redux because, well, if we have Thermite for React, then we should have Redux. And it's using the free monad for a DSL and a Cofree Comonad to implement the interpreter. And there are two interpreters: one that runs in the front-end application, and a little bit different interpreter that runs on the backend. The difference between those interpreters is that on the front end you want to pass the changes back to the backend, so you want to have asynchronous communication with the backend, that you send the command. It actually sends the command down to the same command down to the backend. And to see that, can I React? So if you go to home, you can see that it mounts the home route. The browser router is a component that is provided by the library. That is a very simple component that just tracks the changes in the history and reruns the router. And something very, very similar runs on the backend. And if we go to one of those authors, then you have a musician route mounted by the router. I can probably try to show you the code. It will be a little bit difficult because I see it here, not here. Where is the mouse? Oh, it's here. So this is the main function. Where's the important bit? So in this function, we create a store which holds just an array of values, and we find an element where to mount the component. Here we create the store, and here is the browser router class, and it's wrapped with some other component to take to look at the changes in the state, in the global state of the application. So if you add a person, then the state will change, and it mounts this this component, this CLS class, in the DOM, and then React picks up on that, and the router is on top here. So it's very simple, as you've seen. It's just the home route and the musician route. The first has a very simple parser that just checks if we are in the home and the other checks for the user and parses an integer, so we know which one it is. And the server is a little bit more complicated, I think. Whereas so there are two things in the server, because the server serves here for serving the static files, so the index.html, the scripts, and also as an API. So here you have a very simple router for that server, which here just runs the file server and an API. And the rest is for the app request, and which is here. And when an application comes, or when we have a request for the application, it will just it will render this piece of HTML, which is just the head and the body, and it will render the React application into a string, and it takes and the rendering of the application is here. Just React provides this render to string. It creates element, and the entry class is a very simple class that just runs the router, and that's basically it. There is also this API part, where it is handle. Yeah.
So it seems like you're being stored as an interpreter.
Yes, exactly. It's
so being a Comonad is like very untitled effect, right? It's like uneffectful as it can be, because it's a Comonad.
yeah.
And monads are effects, Comonads are unaffected.
Yes,
right?
stream of values, basically.
Right. So that's, I guess, this great pairing between monad and Comonad, free Cofree, and store and state.
Yeah, exactly.
They pair very nicely because that kind of dual in the very sense of.
Yeah.
But that makes, in general, not. You want to have stateful. You want to have effectful interpreters in general, right? Typically, when you program, you want your interpreters to have access to all the effects you need.
Yeah.
And that kind of prevents the typewise from getting there. So can you come on this, like, would you like if Pures could use the FFI hacks to basically get effects even though the type system tells you, hey, I'm a Comonad, I'm not effectful. Would you do stuff like this? I don't know if I'm asking my question. So
Yeah.
When I try to use Comonad as interpreter, I'm struggling with not being able to do much. Because I cannot do an I/O, I cannot do a database communication, I cannot do anything.
You can do that, but you have to explore. There is this in PureScript. There is this explore function that lets you explore Comonad through a pairing monad, and you cannot use effects with that. But you can tweak this function, and I made a pull request that was accepted, where you can actually explore in some monad. For example, in F or AF or whatever you want.
You basically detect system node exposes the files.
It does. It does. Yeah. I believe it does. We can sit later and look at the code. It's easier.
You use the extend and implement it. It also gives you ability to use like monadic computation in omnichannel, right?
Yeah.
So I'm wondering about performance in with having the Cofree structure around your routes. Have you considered, or would it be possible to record certain types of performance data about how long it takes a component to load, or how many SQL queries happen for that component and its children, and be able to retain that? So if you wanted to debug performance.
Yeah. I have an answer that is not straight, because I wrote this library to use Cofree Comonad as an interpreter for basically like a Redux store. And what I discovered is that you actually can add other things that the interpreter can do by hoisting the interpreter, like logging, things like that. And possibly you can add things like checking how long things take. Yeah.
I could see that being extremely beneficial for developers.
Yeah.
Maybe you could compose your Comonad interpreters such that if you're wanting to retain some additional data that's more expensive to calculate, as a developer, you can use the developer interpreter, Comonad interpreter, which would also compose the regular interpreter that a client would see.
Yeah.
And be able to stack your annotation data.
Yeah, exactly.
That'd be really cool.
Could you show the spot in your code where you use the same DSL, same Redux DSL that you interpret differently on the server and on the client? That's cool.
Yeah. Just so. It's not here. It's here. So the DSL has just two commands: add musician and remove musician. And actually, the interface, the application only is using add. And if we want to play with free monads, we need a functor. So it has a functor instance. It has also encode JSON and decode JSON because we want to pass them through HTTP. So we have to somehow do that. So JSON is a good way. And the DSL is just a free monad spun by this functor. There are these two functions that can be used to act. This add musician, which is lift F over add musician, and remove musician, which is lift F, which we've seen already today in the morning. And then where is and the interpreter on the front end so it's a new type, this run up, and it has to be a dual functor that we will be able to pair with the functor at the beginning. So that one was a sum. So here we have a yeah, that one was, yeah. So here we have a product, and then you usually make an interpreter using this unfold Cofree function from the Cofree library. With the next is a function that recursively creates the Cofree Comonad, and let's look at the end first. Where is the so the next function, it just takes the state, which is array of musicians, and returns the Cofree, and it is just run up of add musician of state and remove musician of state, and these two functions are defined here above. And let's just see what is the add musician, what it does. And as you can see, it will return something in AF, so it will be effectful. And what it does, so this application makes one thing that it does, it updates it will update the store of the application, but also make a request to the API to the backend to do the same. So when you reload the page, you still have the musicians that you've added. And yeah, and that's it. There's on error and on success. Like if there was an error, you want to revoke the action that was taken, and if there was success, you also want to check if it was right or wrong, or what was the response, and that's it. And the interpreter on the server side is actually simpler. I don't use a Cofree. I just use two functions that interprets that functor. Yeah, there's a reason which is written here. That yeah, but that's it basically. This code is on GitHub, and my talk is also on GitHub. So if you check COOT on GitHub, it's there. That's all. Any more questions? Okay.